So don't say anything crazy. Make sure I'm recording. Okay. So, all right. I talked about binomial probability distributions. I kind of skipped the initial stuff with this, which is straight probability distribution tables. And I might have, from what I remember, briefly talked about this, I want to say last week, when we did an example with the frequency table and I talked about the relative frequency. And I was like, you're going to see this. And we did like different, anyway, not everybody was there, so whatever. But probability distribution table is kind of like a relative frequency table, actually. You have X, which is your random variable. I don't like my arrow. Which is your random variable representing all your possible outcomes. And for now, X is a discrete random variable, which means you guys, for this week, are only having outcomes that are finite or countable. So they're only whole number outcomes here. Okay? So X is a discrete random variable. It represents all the possible outcomes of whatever procedure you're doing. And I'm just going to make up some stuff. Let's say, you know, these are my outcomes. I'm going to make up whatever. The right-hand column is the probability of each outcome. So the probability that I get 0, let's say out of 3, whatever, I don't know, I'm making up, is 0.1. Let's say this probability is 0.2. Let's say this one is 0.3. Obviously, because the probability of each outcome is a probability, all these values have to be between 0 and 1. Unless they're in percentage form, then they're between 0% and 100%. But a probability distribution table is typically with decimals, just like relative frequencies. Remember relative frequencies? These are like relative frequencies. The other requirement for a probability distribution table that's very important is, you're going to see this notation, the sum of all the probabilities. Remember this sign? I've said it before. I've used it before. This is summation. It means sum. The sum of all the probabilities is equal to 1. So you have a couple questions that's like, how do they ask it? Complete the following probability distribution table, and they give you all the stuff and they go, hey, what's this one? Well, because this all has to add up to 1, the sum of this whole column has to be 1, and so far you have 0.1 plus 0.2, 0.3 plus 0.3, 0.6. This has to be 0.4 in order for it to add up and be 1. This whole column. Okay, so that's easy. Those are nice giveaway easy ones. Okay. So this is an example of a probability distribution table. Now, you might be asked to create one like this. This is asking you to create. Let me just change. I think your numbers are probably changed. I'll just change some of these numbers. I don't know, I'll leave it. I think yours are going to be different than mine anyway. This one. Suppose that you were offered, this is like question 5 in the first homework assignment, okay? And I'm going to do a couple things with this. I might add, oh no, they ask you for expected value. That's what I'm going to do anyway. So suppose that you were offered the following deal. Thank you. If you roll a 6-sided die, if you roll a 6, you're going to win $11. If you roll a 3, a 4, or a 5, you win $2. Otherwise, you pay 10. With my luck, I'm not playing that game. I don't know about that deal, guys. Come on. But if you're a lucky person, or you practice, you roll a 3, you roll a 6, you might, that might be good. This does not sound like a good game for me to play. Now, you're not paying to play this game. You're just paying if you don't roll one of those other things, okay? So complete the binomial probability table, list X values, where X, now they tell us what our random variable is going to represent. X is the profit from smallest to largest and round to 4 decimals. So I'm going to create my table. And if it's a probability distribution table, I have all the possible outcomes here and their corresponding probabilities here. So what are all the possible outcomes? Now, X has to represent profit. or at least, you know, now I'm not paying anything. It's not like this is a raffle where I have to pay for a ticket and then win something. I think there was an example, maybe what we did in past assignments. I don't think. Oh no, there is one with that. Maybe I'll do that tomorrow. Maybe I'll do that tomorrow. There is one. Yeah. Yeah. Haley, you got that right, Haley?
What?
The question
Got
you
what?
sent me? You got that question you sent me, right? That makes sense now?
Yeah.
I saw it a little postponed. I'm sorry.
Okay.
Okay, good. So what are my outcomes? I'm not paying for this game, but I'm either gonna win 100. Wouldn't that be nice? I'm gonna win $11. That's positive. Or I can win $2. That's positive. Or I'm gonna pay $10. That's negative. Now, it doesn't matter how you represent the outcomes, but because they said from smallest to largest, I have to pay attention to how the order I'm gonna put them here. So the smallest outcome is paying $10. So that's negative 10 because I'm not paying anything for this game, but if I don't roll one of these other scenarios, I owe whoever this person is $10, and they're gonna probably be making some bank on this game. If you roll a 3, a 4, or a 5, you win $2. So that's positive, right? And then if you roll a 6, you win 11. So that's positive 11. So here, this one was rolling a 6 is just for your notes. This one was rolling, what was it? It's a 3, a 4, a 5. So all the other outcomes would be rolling a 1 or a 2, right? I didn't miss anything. 1, 2, 3, 4, 5, or 6. So that's what each one of these represents. So if I roll a 1 or a 2, I'm paying 10. If I roll 3, 4, 5, I'm getting $2. And if I roll a 6, I get $11. Those are all the possible outcomes for this particular procedure. So that's what this represents. So you see like all the possible outcomes, and each one of these is technically like a discrete random variable type of situation. No decimals, right? As your possible outcomes for your random variable. Now I have to figure out the probability of each of these. So I'm gonna write notes here. The first one would be the probability of rolling a 6-sided die once, just once, and getting a 1 or a 2. I don't know if you remember this, but you're not rolling it more than once. So there's no multiplication rule. It's out of 6 total outcomes because it's a 6-sided die numbered from 1 to 6. And there's 2 outcomes for this, a 1 or a 2. So 2 out of the 6 represents my first probability. Tell me if that makes sense. Now let me see if they want it in fraction or decimal form. I can't remember. Decimal. Round 2, 4 decimal places. So this is 1/3, which is 0.33333. Okay? Color coordinate this. Let's do pink next. This one is pink. 3, a 4, or a 5. So the next probability, I would win $2, but that would happen if I roll a single die once and I get a 3, a 4, or a 5. Again, I'm only rolling it once, so it's not multiplication rule or anything. And then how many outcomes? 6 total outcomes, but for this particular case, 3, 4, or 5, there are how many on top for my numerator?
3.
3.
Yeah, good. 3. 1/2, which is 0.5. Okay. Last but not least, this one would be rolling a single die once and getting a 6. What's that probability?
1 out of 6.
1 out of 6. 6 total possible outcomes. Only 1 is a 6. Actually, I don't remember what 1/6 is. Let's see. 1 divided by 6. 0.166 blah. So rounding this to 4 is 0.1667. So approximately 0.1667. And notice that the sum of these This is your quick check to make sure you did your table right. 2 plus 3 plus 1 is a total of 6 over 6. Or if I add up, and I'll show you, if I add up 0.33333 plus 0.5, which I'm getting from this column, and then this one, plus 0.1667, I should get 1 or very, very close, like 0.99 or something. Otherwise, maybe there's a rounding error or something. So the sum of this column is 1. And that's an indication to see like if you did something right or not. Check that, make sure that adds up to 1. So that's what a probability distribution table is. All the possible outcomes for a procedure. The procedure here is rolling one single die, one time. These are all the possible outcomes you can get in this particular case. Profit, you would win or lose. And then their corresponding probabilities. And the reason this adds up to 1 is because it represents the total sample space, the probability of the total sample, you know, everything all together, which should add up to 1. Tell me if that makes sense. Any questions? Yeah. Are we cool? This one I want to do, find the expected profit. Round to the nearest cent because it's expected profit. So expected value, let me write notes over here on the side. Mean, which we know is like average, right, is the same as expected value when you're doing probability distributions, okay? Which is represented, if you ever see it in notation, capital E of X. On average, if I continue this type of procedure, what would I expect my outcome to be? Or what is the expected outcome on average? That's basically what expected value is. So like, how much money do I expect to either make or lose on average if I play this game? So there are two ways you could find this. One is sometimes using the formula is faster, but there's a calculator thing we can do too. But to find the expected value, you would take the sum, and this is the, which is also, known as the mean of the probability distribution. You would take the sum of all the random variables times their corresponding probabilities. And you could do this either by hand, or you could do this with the graphing calculator. I'll show you both. But if they ask you for expected value, it's the same thing as asking for the mean or the average outcome. On average, what would I expect to be? So find the expected profit. Same thing as finding the expected value. And so if I use the formula, which I'll show real quick, because sometimes you might want to do that by hand, could be faster than by a calculator. You take each of these random variables and multiply by the corresponding probability. So -10 times 0.333 plus 2 times 0.5 plus 11 times 0.1667. Okay, that's all the formula is asking you to do. Multiply each of these and then add them all up. So multiply your rows and then add it up. So I'm going to show you that, and then I'll show you how you can also do it on the graphing calculator because it applies to something we did before, which I'll refresh your memory in that. Yeah, let's do that. Okay, parentheses, -10 times 0.3. Let's see what we do. I'm assuming on average we're losing money on this game, but plus 2 times, make sure you put parentheses around the multiplication because I want multiplication and then addition. 11, I'm just going to put it as I wrote it. Yeah. On average, I'm expecting to lose. Round to the nearest cent. So if I'm rounding to the nearest cent, it's like saying 0.4993 cents. That doesn't make any sense. If I round that to the nearest cent, it's about 50 cents. I'm losing. It's negative, right? So on average, I'm losing 50 cents if I keep playing this game. Which, I mean, looking at the game, I probably expected to lose more than that. And then look, this is not considering luck or the die or whatever, or like, you know, it should be a flat table, it should be a even, you know, a fair die, but you know what I'm saying, like, this is not including luck. This is on average. If you keep playing, if we go statistically speaking, we're going to lose money. So I would probably not play this game because on average, my outcome would be a loss. So I think it says interpret the expected value. If you play many games, you will likely lose on average very close to 50 cents per game. Based on the expected value, should you play this game? I would probably not. No, since the expected value is negative, you would likely come home with less money if you played the game before you left. So this is my expected. Now, any questions yet? Just to refresh, this is actually going to be the same thing if you're using the graphing calculator trick as finding the mean of like a frequency table, if you remember that, which I would have to input both of these into my list to have it calculate the average for me. So let me show you how you can do that if you want to do it that way. You go to stat, and this is a good refresher, edit, and this is for me to input, you know, these guys. So I'm going to put in L1, let me get rid of this stuff here, clear, enter. Let me get rid of this stuff here, clear, enter. So I have nice clean. So L1 is my X's, and I have a -10 there, and I have a 2, and I have an 11. And then my outcomes, I have a 0.3333, and then I have a 0.5, and then I have a 0.16. So this is like a frequency table, relative frequency table, right? And I want the mean of it. Do you guys remember how to find the mean of a relative or of a frequency table or a relative frequency table? Do you remember where you went? I'm not mad at you if you don't. That's why I'm refreshing your memory too. Stat. And then, listen, you need to write yourself notes, calculator trick notes. You should have a formula sheet, reference sheet for yourself, a calculator trick sheet, reference sheet for yourself, right? So you should be like, all right, let me go to my calculator trick sheet and see what she's talking about. Finding a mean of a frequency table. Oh, stat. Oh, calc. Oh, 1 bar stats, if you remember. Just like when we found mean and standard deviation by the calculator. This is how you do it with a frequency table or also a probability distribution table, because my list in L1, my frequency list is like my relative frequency, L2. Yeah. And then calculate, I should get the same thing. X bar, my sample mean. Boom. Now, same thing that I got by doing it here. Also, by the way, if you're ever asked for the standard deviation from a probability distribution table, this is it. Notice SX is not here because a probability distribution table represents all the possible outcomes. So you can assume that you're, you know, focusing on like a population standard deviation. So this is the standard deviation, which is kind of large, which I would expect, right? Because you know, everybody obviously is going to get some randomly different things. Some people are going to win 11, some people are going to win 2, and some people are paying 10. So I would expect the standard deviation to probably be some high. But this is what we're asked for. Expected value is the same thing as the average or the sample mean. And yes, you're allowed to bring, I think, a 3x5 flashcard to the final. Flashcard, did I say that right? Yes, and I think front and back. So start setting up for that. Start setting up for that now, because then you can also star the stuff that you forget. You know, some of these calculator tricks you're probably just going to remember. It's not going to be an issue. Some of them maybe you're going to be like, every time, yo, I just keep forgetting that one thing. That's what you're going to need to write on your flashcard. All right, wait, let me stop recording real quick and then ask if you guys have questions.